We'll do a quick revision of what we have discussed in last class and then proceed with the remaining topic on the gas refrigeration cycle. So in last class, as far as VCRS goes, we were discussing about the connection between the internal and the external regime. The internal regime is nothing but your refrigerant. The external regime is the substance which you have to cool and the substance to which you are re releasing heat. So it could be refrigerated space, or it could be water, it could be milk. Okay, so that is the external regime on the refrigeration side, and on the heat rejection side, again, it could be air, water, where you reject heat. Okay, and in that we were discussing that if you even have all the four processes of a Carnot cycle, as far as the internal regime goes, the external regime will not have these isothermal, so this is TS. So it will not follow these isothermal lines. The external regime will have a finite m dot into Cp, and hence the external regime will follow something of this nature. So this would be the process line on the external regime side. So if you have your evaporator temperature, let's say 10 degrees C, the external regime may go from, let's say, 20 to, at best it can go to 10, maybe it will reach 15. Okay, similarly, if your condensing temperature is 50 degrees C, it will only be sustainable if your ambient temperature is, let's say, 35, and it goes from 35 to 45. Some arbitrary numbers I am giving you just to give you a feeling that you require 5 to 10 degrees C of delta T for proper heat transfer if you have a finite size of the heat exchanger. Okay, if you want to have heat transfer across a very small delta T, you will see your heat exchangers will become extremely big. Okay, so from technical point of view, there is nothing which stops you from having infinite surface area, but then you look at the capital investment that you will have to incur for that. So you will always have some delta T between the internal and external regime, and you will see that the external regime, as long as there is no phase change in the external regime, you will have such process lines. Now, once we know that the external regime is going to undergo some sensible heat transfer, so is this the best cycle? So this was one of my questions which I had posed. Nobody answered in the class. I asked you to think and maybe come back next week. So if you have thought about it, well and good, because it is a part of one of your tutorial problems. So once you know that your external regime follows this path, will this cycle be the best from efficiency point of view, or can you come up with a cycle which provides you the least amount of irreversibility? So this huge delta T between the internal and external regime creates irreversibility. And you can see that in order to maintain 20 degree to 15 degrees, so you are cooling air from 20 to 15, you are still maintaining an evaporator temperature. At best, you can maintain 15. You cannot go higher than that if you want 15 degree as the outlet air temperature from the heat exchanger. You cannot maintain an evaporator temperature of 16 because it will go above the 15 degree line, and you cannot have the heat transfer process lines crossing each other. So then can you come up with a better process on the heat transfer side which will minimize these irreversibility? Okay, then we moved on to the actual VCRS cycle. And your actual VCRS cycle without the dome I am drawing, it will look like this. Okay, and now if you have your process lines on the external regime side will look like this. And we discussed something called as a pinch point. Pinch point is that point or that location in your heat exchanger where you have the least or minimum delta T across the two fluids, okay? So if you have this is the fluid which is hot and this is the cold fluid. So wherever you have the least temperature difference between the hot and the cold side, that position is called the pinch point location, okay? And whenever we design a heat exchanger, we have to take care of that particular location. The pinch point should not go to 0. That delta T should not go to 0. So normally the designers maintain around 2 to 3 degree temperature difference at the pinch location, and then we design the entire heat exchanger. Okay, so you cannot have your air or the external regime on the condenser side going like this. Okay, in fact, you cannot even have it just touching it. So that is the limiting case. Okay, but then you will not have any heat transfer across this point. So we maintain some finite temperature difference over here. Now, there is nothing which stops us from subcooling also. So in fact, we can also subcool it. Okay, but the subcooling limit will be whatever this air inlet temperature is on the condenser side. So if your ambient temperature is at 35, so that is the limiting temperature to which you can subcool. Okay, please remember this temperature is not the condensing temperature. Condensing temperature is the temperature or the isotherm denoting this two-phase region. Okay, so it could be 50 or 45, whatever, based on this pinch point. So you can see that you can go up to whatever the inlet air temperature is, but you cannot go further. And hence we had discussed that we can go for an LSHX system in case we want further subcooling. Similarly, in the evaporator side also, the refrigerant need not exit exactly at x equals to 1, that is saturated vapor. It can also undergo some amount of superheating. So this is not the useless superheating which occurs between the ambient, that is outside the refrigerated space. So this is still occurring within the refrigerated space only. So that is your indoor side or your freezer segment. Okay. So again, over here also you can have such a limiting case. So these are just few things which we can quickly determine if we know what is the m dot air into Cp. Okay, and if we know the inlet air temperature, okay, and the temperature to which we have to cool this air. So based on these things, we can find out what are the limiting cases. So in case you are designing your heat exchanger which accommodates some superheating, so at best what you can do is you can have superheating up to the ambient or not ambient, I should say the refrigerated space temperature. Okay, so this is your indoor or refrigerated space. Okay, this is your outdoor or fluid to which you are rejecting heat. So these are the limiting cases from heat exchanger point of view, and that is what decides now the entire cycle, and the connection is there between the internal and external regime. You may have designed it for a particular ambient condition, but when the ambient condition changes, your design based on the design of the heat exchanger, these lines will also shift up or down. So if you have an AC which has been designed for, let's say, summer condition of Rajasthan, and if you operate it in, let's say, Shillong or Shimla, so the ambient condition changes, and hence these lines will shift down. It will not operate at 50 degrees C condensing temperature just because you have designed it for that. Someone's mic is on. Someone is enjoying music, which is not sung by Lata Mangeshkar. So if you operate your heat exchangers in different conditions, because there is a connection between internal and external regime, your operating conditions on the refrigerant side will also change. That is the most important thing that we must understand. So the design or sizing of the heat exchangers is also critical. Most of the air conditioning systems that we used are typically designed for 52 degrees C. You will see that label. So this system can operate at even 52 degrees C ambient condition. So we are uh, designing it for the most extreme case. We will not have 52 degrees C temperature, at least not till now. Maybe global warming can push the temperatures beyond 50, who knows. So at least in India, we do not see temperatures beyond 50, but we are designing our systems for such extreme cases. Now, if you operate your system at uh, a location where the ambient temperature is 30, so this line will be pushed down. Okay, and the slope of the external regime and the entire process line, how much of subcooling will happen, what would be the temperature difference between these two internal and external regime will be governed by your heat exchanger design, because that is not changing, that is fixed. Okay, similarly on the evaporator side, if you have designed it for say 10 degrees C operating condition, where you assume that the refrigerated space would be at around 16 degrees C, that is the least temperature setting that we have in the AC remote. Now, when you are operating it at 25 degrees C, this line would be pushed up. Okay, so this entire cycle is not decided by not just by how we have designed it, but it is also decided by what is the current condition. Okay. So this is where we had stopped. No, we also discussed something about the non-idealities in the VCRS cycle. So in the VCRS cycle, we discussed that this.
Excuse me, sir.
Yes.
Sir, if we don't have the isotherm, rather we have a line in condensing region.
Mhm.
If we have a negative slope of that line,
Something of this sort.
no, the superheated horn is the same, but the isotherm line is having a negative slope.
Like this.
Yes, and so then can the this line cross the pinch point?
So you are saying that the condensing side temperature is increasing. So the hot side fluid is getting heated up.
No, sir. My that's okay. That will not be good. But the external, the heat sinks can the line across the pinch point, because we are using a counter flow like heat
So you're
exchanger.
talking about like this. This is the
Yes,
external region. Not possible. Not possible. This 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 entire region is not possible.
sir. But that part of the uh, sink is not connected. I mean, is not in contact with the same line, because the flow is reversed.
No, flow is like this and it is like this in this fashion, isn't it? And this is the flow of the external region. I didn't get your question then probably.
Okay, yeah, yeah, I got confused with the heat exchanger
Okay,
type. Yeah.
okay, okay, okay. So suppose, see external regime, suppose if this is the slope, automatically the back pressure on the compressor will increase and your cycle will move to this. You don't have to do anything. See, the natural process is there will be a temperature difference between the hot and the cold fluid. So your external regime is the cold fluid in case of a condenser. So that is where you're ejecting heat. So if the ambient temperature moves let's say you have designed it for this condition and it is operating in a climatic condition where the external temperatures are higher. So it moves up. Automatically, the condensing temperature will also move higher. You as an operational person, you don't have to do anything. It will automatically set at a particular delta T, a positive, of course, a positive delta T between the hot and the cold fluid, and you will see that the condensing temperatures are now higher. And that will increase the back pressure on the compressor, and hence your compressor will be doing more work. Does that clarify your doubt?
Yes, sir. Yeah.
And I think I also told that the primary difference that we think between a 5-star and a 3-star AC is the compressor efficiency, but that is just one part of the story. The second part is also the heat exchanger. So your 3-star AC will have, let's say, some surface area. Your 5-star AC will have, let's say, 1.3 times the area or 1.4 times the surface area for heat transfer. So you can work now across a smaller delta T. So even when your ambient temperature is, let's say, 40 degree, and this is uh, the operating condition of a 5-star AC. This is, I'm just focusing on the outdoor unit. For the same condition, your 3-star AC, because it has lesser surface area, it will work across a larger LMTD. Or in this case, just if you don't understand LMTD, just focus on the delta T. So it will operate at a higher condensing temperature. So this delta T gets fixed by how much surface area has been provided for heat transfer. And if you provide infinite surface area, you will see that this line and the condensing temperature lines are very close to each other. Okay, you will approach that limiting case of pinch point temperature difference tending to 0. Okay, so you will require very large surface area. So performance will be improved, but you get diminishing returns. You can check how much more you need to invest in addition to what a 3-star AC will cost. And you can see that you will require several years of operation to break even. So that is how you can do an economic analysis. So if you are operating your AC maybe only for a few hours in summer, it doesn't make sense in investing in a 5-star AC. But you are operating it, maybe your summer periods are very long and you're operating almost 24 hours a day. So let's say now an office or a commercial building, it makes a lot of savings if you invest initially for an efficient system. An efficient system is not just an efficient compressor. It is also the heat exchanger design. Yeah, because that is finally setting your evaporator and condensing temperatures and hence the pressures. So if your evaporator temperature goes low for the same refrigerated space temperature, so let's say you want to maintain 16 degrees in a particular room. In a 3-star AC, your evaporator temperature could be of the order of 7 degree, whereas in a 5-star AC, your evaporator temperature could be of the order of 10 to 12 degree. That is a huge benefit. So now your compressor will work across a smaller delta P. Okay, so what you see in your power rating is not just the efficiency of the compressor, but it also the efficiency of the heat transfer process, which then comes out as an outcome as savings in energy. Okay. So yeah, so the last thing that we discussed in VCRS system was the actual cycle. So this is the standard cycle that we had been discussing. This is how your dome is. So you will have saturated liquid at the condensing end, saturated vapor at the exit of the evaporator. So sometimes this is also called as the single stage saturated cycle. Single stage saturated cycle. So single stage because it is only a single stage compression. Yeah, there are multi-stage compression cycles, but we'll not have time to discuss about them. So normally when you have to go to very low temperatures, much lower than -40, -50, even there are systems which operate at -100 with VCRS cycle. So then there are various ways of splitting the compression process. So they are multi-stage cycles. So what we are discussing till now is single stage cycle. And if you have saturated liquid and saturated vapor at the two ends of the heat exchange process, so then it is called single stage saturated cycle. So so this standard cycle, if you deviate, you can have some amount of superheating here, some amount of subcooling here. Okay, this is what happens in all our refrigerators and residential air conditioning systems. So they are not operating at the standard conditions all the time. Okay, so this becomes your modified cycle. Now this superheat can either come from the refrigerated space, or it can come because of poor insulation, or it could be because of an LSHX that is placed in the system. Could be any reason. Okay, now if you also look at the pressure drop that happens as refrigerant flows through the tubes and as it flows through the valves and the suction port, the discharge port of the compressor. So then once you start accounting for all those non-idealities, then the cycle doesn't look this simple. Okay, and if you include the non-isentropic process in your compression also, so then the cycle looks something different. So you will have some amount of pressure drop in your evaporator. You will have some amount of superheating. You can have partly useful superheating and partly useless superheating. Okay, when you come to the lab class, we will see that in case of hermetically sealed compressors, you cannot avoid the useless superheat. Okay, then you can have some pressure drop again in as the vapor enters the compressor. Okay, because of the pressure losses in the valves, and also there are pipings inside the compressor assembly itself. And then you, instead of going an isentropic compression, you will undergo some non-isentropic process. You will end up somewhere here. You will have a larger superheat. Now, remove this. You will end up somewhere here. You will have larger superheat at the exit. So you can draw any dotted line. You can draw like this, because we don't exactly know what the process line is throughout the compression process. You will end up here. Okay, and then again you can have some amount of pressure loss over there as the gas comes out of the discharge valve, discharge pipeline, and then this would be your condensing. So your condenser may also have some pressure drop and some amount of subcooling, and then so your cycle could look significantly different from the standard cycle that we have discussed. Okay, so we don't have to quantify all those things. It is just to tell you that the cycles will have a lot of non-idealities which we are not taking into account while performing the thermodynamic analysis. So any doubts till now? Hope the power has returned. Yes.
Yes, sir.
Yeah. Okay. So then we moved on to the air cycle. Okay, and so instead of air, we can use any gas. So generic term would be a gas cycle, and we are discussing only refrigeration cycles. So one cycle which we had looked at was the reverse Brayton cycle. And I told you reverse Brayton cycle is very similar to the VCRS cycle. Only thing is, instead of operating near the dome, we are operating far away from the dome. Okay, where there is no phase change, and you can treat the gas almost like an ideal gas, and we can do certain simplifications and quickly perform the analysis. So finding the COP of the system and all, I did not discuss because that is straightforward for a reverse Brayton cycle. So what is more important is where do we use it? And do we use again the standard reverse Brayton cycle, or we use some modified form of that? So we were discussing about the one application being the aircraft air conditioning system. And why we use air as the refrigerant over here, over there is because air is already there present in the engine, and the jet engine is already compressing the air. So we can take help of that air itself to perform the air conditioning. Okay. So previously people attempted to use VCRS in case of the aircraft air conditioning system, but the major limitation was this is a closed cycle. You cannot spray refrigerant into the fuselage to perform the cooling. So this is a closed cycle. So you will require the heat exchanger in the evaporator side, just like what we have in a split AC. Okay. You will also require a separate compressor. Okay, so you have to carry all this closed loop system along with your aircraft. This is one issue. The second major issue was once the aircraft goes to a cruising altitude of 30,000 feet, 32,000 feet, the air inside the fuselage is at very low pressure. So you require to deliver air at 0.8 to 0.9 bar, whereas outdoor the pressure would be 0.3, 0.4 bar. So you have to deliver pressurized air. So if you were using a VCRS system, it will not deliver a pressurized air. It will just cool the air present in the fuselage. And you still have to additionally provide the pressurized air. So the initial aircrafts which attempted to use VCRS system, they were limited. They had a limitation on the cruising altitude. They cannot go above a certain altitude because these systems cannot provide pressurized air. So that's why we went to the air being used as the refrigerant itself, because now we can operate it in an open cycle. So once we get the cold air, we don't have to cool air with air. We just directly provide or deliver the cold air, which is also pressurized. Okay, pressurized cold air. So your air conditioning system in an aircraft is performing two important things, not just to remove the heat that is generated, but it is also delivering the precious air which you can breathe. Okay, so this air has to be pressurized, and hence if the aircraft air conditioning system fails, there are certain protocols which the pilot has to follow. First of all, you will see that the mask drops, and then you will see that the pilot has to make a steep descent to around 8 to 9,000 feet, which is tolerable for majority of the human beings to breathe comfortably. So 8,000, 9,000 feet is slightly above Gangtok, or maybe, I don't know how, at what height Shimla is. So maybe around that height. Okay, but still people with asthma and all will find it difficult to breathe. So the aircraft air conditioning system is very, very important, and it has to be very reliable. So what we do in case of aircraft air conditioning is we already have the engine. So the engine is following the Brayton cycle. Okay. So the engine is following compression, heat addition, expansion. Okay, and again it is an open cycle. So heat rejection is just happening by dumping the hot gases from the exhaust. Okay, so this compressor in your jet engine is being driven by a turbine. Okay, and since our main aim is to provide thrust, so we do not extract all the power in the turbine, we extract only that much which drives the compressor, and the rest is what is providing thrust. So this is your jet engine Brayton cycle. Now this compression itself happens in multiple stages. So we have multiple, you can see multiple sets of blades, which is compressing the incoming air. Okay, and somewhere in between we take the bleed air out from this compressor. So let's say this at this point we take out the pressurized, mildly pressurized air, and we use this air for air conditioning. Okay, we do not take this air. Okay, so you will have a set of low pressure compressor and then a high pressure compressor, so you can bleed air from in between. Of course, you do not have the provision of changing the location continuously. It's a fixed pipe from where you are taking out. And once you take this air out, it is already significantly hot, I must say, and pressurized. So this is your engine. So your aircraft air conditioning system is taking air at this point. Okay, so first it cools this air, isobaric cooling, and then we compress it again, cool it again, and expand it in a turbine. So if this point is 2 bar, okay, so if this is 2 bar, so this is your 2 bar. So we are bleeding air at 2 bar. First we are cooling it down, then pressurizing it, let's say up to 3 bar, again cooling it down, and then finally expanding it in the turbine. Okay, this turbine now drives this compressor, and we get around 1 bar air over here. Okay, so this first initial stage of compression is already done in the engine itself. Okay, and what is the suction pressure at the engine side is around 0.3 to 0.4 at cruising altitude. Okay, so this is the cycle which we were discussing in the previous class. So we bleed air, pass it through a primary heat exchanger. Now this cooling happens again with the ambient air, which is available at around minus 40 degrees C, because at such altitudes the temperatures are very, very low. Okay, and we have these air inlet ports for the heat exchanger. So you will see that at the bottom of the fuselage, there are certain ports which are provided. Okay, and then we pass it through a compressor, again cool it, and then pass it through the turbine. So the idea is still the reverse Brayton cycle. It is just that we are having multiple stages of compression and one stage of expansion. Now this is still a simplified form of the air conditioning system. We have a lot of bleeding going on from here, okay, just to ensure a certain set temperature is available always. So it need not happen that the air after expansion from the turbine will be at exactly the desired temperature. So we may have to mix it with some amount of hot air, which is bled after this primary heat exchanger, and we may have to mix it to reach the desired temperature. So air after the expansion process could be very cool. So it may not be comfortable for us. Okay, so there are a lot of other valves and instrumentations. There could be certain purging process which is also going just to control the amount of mass of air which is being fed into the cabin. Okay, so this looks as if whatever mass has been bled has to be put back into the cabin. It is not like that. We can also purge some air into the ambient in case the required load on the air conditioning system is less. So we are not looking into the detailed instrumentation layout, which helps us match the load always. Okay, after expansion through the turbine, there could be even tiny drops of ice which forms because the air becomes so cool, and the moisture inside the air, it can even freeze. So that's why some portion of the hot air is also mixed along with this air which comes out after the turbine. And this entire assembly is on a single shaft, and it is called the air cycle machine. You can see the air cycle machine over here. And these things are all big heat exchangers. And these pipes are huge, you can see. So as I have already told you that whenever you have poor density, you have to go for higher pipe diameters. Okay, if you have small pipe diameters, you will incur a lot of pressure drops. Okay, so this air pack, pressurized air conditioning kit. So this pack is there on both the left and right hand side of the wing. And once you're providing pressurized air into the cabin, you also have to take out the air. So you can always visualize an aircraft as a balloon which is continuously being pressurized and depressurized. So depressurization will happen through the small leaks in the door. Okay. Uh, and of course, you also have an active outflow valve. So the leakage is not under your control, but how much air will escape through this outflow valve is under your control. So the control of this outflow depends on the quality of air which is there in the cabin as well as the pressure. So you have to maintain a steady pressure and a steady amount of oxygen content, or you can say carbon dioxide content in the cabin air. So this is the entire process drawn on the TS diagram. So you have various isobars like this. So this P1 is the pressure which is available at the inlet to the engine. P2 is the pressure at which you are bleeding the air from the engine. Okay. Then it undergoes this isobaric cooling in the heat exchanger. Then we further compress, then again cool isobarically, and then we finally expand it. And this P6 is the cabin pressure. And then I think we had stopped over here where we discussed that when the aircraft is on ground, then you do not have the provision of engine running. So your air pack is not operating. So you have to rely on external source for air conditioning, and that external source is a diesel generator driven VCRS system. Okay, so what you see as yellow pipelines are for air in and out. Cold air coming into the aircraft and warm air coming out of the aircraft. So you have an external source which is providing the air conditioning. So any queries?
Sir, is the reverse Brayton cycle the more efficient one in heat transfer between the sinks and internal regime?
Okay, so no, because whenever you have air-to-air heat exchange process, okay, since air has worse thermal conductivity than, so any gas will have a poor thermal conductivity when compared to liquid. Okay, and then further you have to understand that these cooling processes are all sensible cooling processes, whereas in case of a condenser or an evaporator, you have phase change occurring on one of the side. So in case of your residential ACs, the limiting heat transfer process is again the heat transfer on the air side. The heat transfer which is occurring on the internal side, that is on the refrigerant side, that is tremendous. Oh, that is significantly high because it is all boiling condensation that is the major part of the heat transfer process. Whereas now over here you have air to air. So both sides you have air, and of course there is no phase change processes. So your heat exchange process is not as good as your condensers and evaporators in a residential AC. But what we are saving on is the size of the system. Okay, so, and we have completely removed one heat exchanger. Okay, so we are not closing this cycle. We are just straight away pushing the air into the cabin. That is one benefit. And we all, even if you have a VCRS system, you still have to deliver pressurized air for us to breathe, which your VCRS will not deliver. You still have to bleed air from the compressor, okay, at the desired pressure, and then deliver it to the cabin. But once you take air from the engine, it is pressurized, yes, but it is also hot. You still have to cool it. So what we are doing is combining these two features into one kit. Pressurized air and air conditioning, both into one single kit. With VCRS, we still have to have an additional provision for pressurizing it. So as I told you, there were initial attempts to use VCRS because we felt that, yes, the heat transfer processes would be better. But then, of course, we were limited to a certain altitude only. Anything else? So even in this system, you see the heat exchangers are what occupies the large part of the pack. Okay. The turbine compressor unit is significantly more compact. So these heat exchangers are what is occupying large part of the system. Any other questions? Or did I answer what you had in your mind?
Yes, sir.
Okay. So any other questions? Anybody else? So what is very surprising in this pack system is you will see the air at the inlet is minus 40 degree and 0.3 bar. Okay, so we are delivering air to the cabin at around 10 to 15 degrees C. So it is significantly warmer. So if you look at end to end, we have heated the air. But then we have also compressed the air. Okay, so if no other queries, then we'll move to the next air cycle. And that would be the last topic in this module. And the cycle is the Stirling cycle. Okay, so since we are dealing with the refrigeration cycle, so it is a reverse Stirling cycle. Also sometimes called as the Stirling refrigerator. And the application of this cycle is for very low temperatures, cryogenic temperatures. So temperatures of the order of 100 Kelvin, minus 173, minus 180. So where we can store most of the fuels in liquid form. So the cycle itself is very simple, and maybe you would have also studied in your thermodynamics class. So it comprises of two isothermal lines and two isochoric lines. Okay, so if this is your starting position, so 1 to 2 is isothermal compression. Okay, then 2 to 3 is isochoric heat rejection. This is the process. Okay, then 3 to 4 is isothermal expansion. So in this isothermal compression, you will compress the gas as well as reject heat. So I think we have discussed this at length, that whenever we have isothermal compression, it is always associated with heat transfer process. Okay, so similarly, the isothermal expansion will have heat absorption, and this is where we are generating refrigeration. And then 4 to 1 is isochoric heat addition. And now whatever heat we have lost in this process between 2 to 3, we can in fact store it and release it during this heating process, or you can consider this as a heat exchange process between these two process lines. Okay, so this you can have an ideal heat exchanger working between T2 to T3. So your hot fluid comes from T2 to T3, releases heat, and your cold fluid starts at T4, which is equals to T3, and moves all the way up to T1. Okay. So this is going to be an ideal heat exchanger with an effectiveness of 1. But definitely we are not going to have such a device. But if you imagine that you have all these devices available, you have an isothermal compressor, you have the ideal heat transfer device, and then you have an isothermal expansion device. All these things, if they are available to you, you can check that the COP of this system also comes out to be equal to the COP of a Carnot refrigerator, even though the processes are different. But if you evaluate the COP of this ideal cycle, it come out to be T4 upon T1 minus T4, which is equal to the Carnot cycle operating between the same two thermal reservoirs. The process will be different. So how do we achieve all these 4 processes? So this is a very simple schematic to help you understand how this process occurs. So this is a single cylinder, and we have 2 pistons. So you can call this as hot side piston and a cold side piston. Okay, consider that you have your hot side or the ambient over here, where you are going to reject heat, and the cold side where you want to absorb heat to be this side. Okay, so this is the hot side, that is the ambient where you are rejecting heat. This is the cold side, the side where you are absorbing heat. So this is your refrigerated space. You have a single cylinder and 2 pistons, and air is trapped in between these 2 pistons. Okay, and you can imagine you have one crank for this and another crank for this. Okay, so you have 2 crankshafts now, and this will be the BDC for this piston, and right now in the initial condition, this is the TDC for this piston. So this piston can move all the way up till this point, and this piston can move all the way up till this point. Okay, so this is the initial condition. Any doubts here? Okay, so I have not drawn all the crankshaft and all because that will create some confusion. So we are just focusing on these 2 pistons and how the movement of these 2 pistons can help us achieve the processes we have discussed. So now 1 to 2, we have to move in an isothermal manner, releasing heat. So let's say this piston is fixed right now, and this piston moves to the right hand side. So if you had a crankshaft here, so imagine that now from bottom dead center, this piston is moving towards the top dead center. So for some time you assume that this cold side piston is fixed, the hot side piston is moving towards its own top dead center, and the gas which is trapped now in between gets compressed, and it has to be done in a very slow fashion, in an isothermal manner. Okay, and the external regime for this hot side is this. So it is releasing heat as the gas gets compressed. Now, when it reaches certain intermediate volume, you then start moving this piston also, so that we follow the isochoric process of heat rejection from 2 to 3. So now whatever this volume is, we have to maintain this volume constant, and we have to move these two pistons in such a fashion that volume is constant and this gas rejects heat. Okay, so the gas is now passing through some medium called as the porous medium. Now the gas transfers heat as it passes through this medium to this porous medium. Okay, and this volume is same. So the rate at which this piston is moving towards its own bottom dead center has to be equal to the rate at which this piston is moving towards its top dead center to maintain this volume constant. Now, once this piston has reached its own top dead center, this remains fixed now, and this proceeds towards its own bottom dead center. So the cold piston now continues to move towards the bottom dead center, whereas the hot piston is now fixed. So in this condition, you are expanding the gas. The volume of the gas is increasing. And if you have another reservoir over here, you can imagine that it will absorb heat from this thermal reservoir. So you will feel that this reservoir is becoming cooler and cooler as the gas is expanding. And this process again has to be very, very slow, okay, since it is an isothermal expansion. And then now we reverse the process, keeping this larger volume constant. Okay, so now you have air which is trapped in this larger volume, and now you have to bring this piston back to its own top dead center, and the hot side piston has to go back to its bottom dead center, keeping the volume constant. And as this cold gas passes through this porous medium, it will pick up heat which it had released. Okay, so this is a very idealistic scenario that we are trying to imagine. Okay, and the porous medium could look somewhat like this. Okay, so it's a porous cake of metal through which gas can pass. So this completes the entire cycle. So you will have the hot side here and the cold side here. And everything happens inside this one single cylinder with two pistons. Now, as you can imagine that there are quite a bit of assumptions that we have made which are not going to be true in practice. First of all, the isothermal expansion and contraction are not going to happen because we cannot have the movement of these pistons at extremely small rate. Now, why? Can you tell me why we cannot achieve the, because it is not practical to achieve that. Can you tell me what would be the, yeah, someone was answering.
Sir, you can complete your question.
Okay. So can you tell me what would be the refrigeration capacity of this system? This is the cycle. What would be the refrigeration capacity of this system? It will be T4 S4 minus S3. So that is the amount of heat which is being absorbed. Okay, but this is the refrigeration effect. The units of this will be kilojoules per kg. We'll have to multiply that with mass of air, which is there present in this cylinder into something else. What would be that? So we are trying to find out the refrigeration capacity of this system. Units of that would be in kilowatts or watts. Not be kilowatts, watts. So T4 into S4 minus S3 gives you the refrigeration effect, which is nothing but the net amount of heat absorbed by air per unit mass of air. Now, if I multiply it with the mass of air which is trapped inside this cylinder, it just gives me kilojoules. So that is the amount of heat which is absorbed in this region. But then we have to multiply it with something else to get the capacity in watts. What is that? It will be the number of cycles per second. Okay, or let me write it as rotations per second. Okay, now in order to have the isothermal processes, we have to have the RPS to be 0. It has to be very slow. The movement of these pistons have to be very slow. So you will see the limiting cases when you have rotations per second tending to 0. So you can have a cycle which is most efficient, but it is producing 0 watts as the capacity because it is happening so slow. So then it is of no use. The heat transfer processes would be so slow that it becomes immeasurable. Okay, so this is why we cannot have, and this is true for even any other system. So whenever you try to achieve isothermal compression, isothermal expansion by making the processes very slow, you will see that the capacities go to 0. Ultimately, what we want is some certain finite rate of heat absorption on the cold side. Okay, so the refrigeration capacity of an ideal Stirling refrigerator will be 0. Yes, Prakhar, any question? Or you're trying to answer that question?
So I was trying to answer.
Okay, okay. So how do we achieve the motion of the pistons in this fashion? So again, that is another issue. So the piston has to stay fixed at a certain point. Okay, so once the hot side piston reaches the top dead center, it has to remain stable over there. Okay, and similarly, when the cold side piston reaches its top dead center, it has to remain stable over there. So if I were to plot the location of the pistons, so let's trace the hot side piston. So hot side piston at state 1 is at its bottom dead center. So let's call this as bottom dead center. Okay, at position 2, it is somewhere in between bottom and top. And then at position 3, so this is 2, this is 1. Position 3, it is at its top dead center. And then it remains over there in position 4 also. And then it has to come back in position back to 1. Okay, and the vice versa happens for the cold side. So cold side In position 1, it was at its top dead center. So let's not plot it in this fashion. So let's plot this as 1, this as 2, this as 3, 4, and 1. Back. Okay, so at position 1, the cold side was at its top dead center, and it remained at top dead center till position 2. And then 3, it was somewhere here in an intermediate location. And position 4, it was at its own bottom dead center. And then back 1 is like this. Okay, so you will see that this is the repeating fashion of the positions required. Okay, so of course we are going to connect it to a crankshaft, and ultimately what we get is something of this fashion, the sinusoidal form. So we will not be able to achieve the exact positions that are desired from this cycle. Okay, so this is the next set of non-ideality. So these are all from the mechanism point of view. First of all, you cannot have an isothermal process because capacities will go to 0. From mechanism point of view, we will not be able to achieve the exact positional locations that are required for the piston. We will have to make certain adjustments. Okay. And the third is the heat transfer process, where we are assuming that 2 to 3 and 1 to 4 is a heat transfer process which has effectiveness equals to 1. Okay, so the porous media has to store the energy, and of course when it stores the energy, it will store at a particular temperature which is neither 2 nor 3, somewhere in between, and then it will release the heat back in the process from 4 to 1, and it cannot push the gas temperature from 4 all the way till 1. So you will have certain non-idealities over there also in the heat transfer process. Okay, so the entire cycle will not look like this. It will get modified into something else. Okay, so maybe the compression process itself, you may have something of this sort. So this would be the gas heating process. It will not go all the way till 1. Okay, and then the compression process will not be slow. The gas will get heated up much higher than the ambient temperature. Okay, and then when you start the isochoric heat rejection process, you will have somewhat like this. Okay, and then when you are cooling the gas, you may have some process like this. So when you're isothermal expansion, so you may end up something like this. Okay, just I have roughly drawn this. So your COPs will be nowhere close to what we see in the previous slide. So typically they operate at COPs which are 1/3 of the ideal COP, 1/3 of Carnot COP, taking into account all the non-idealities. But the best part of this process is this cycle is you can achieve very low temperatures very quickly. If you increase the rotations per second, the rate at which you cool can be increased. So it's a very scalable system. You can control the RPS. You can have multiple such cylinders to give you more capacities. So let's say you have one cylinder which generates 100 watts of cooling. You place 10 such cylinders and you will get 1 kilowatt. Straight away scalable. And they are very compact. They are very compact. I'll show you the photograph here. They are very compact. So this is around 6 inch. Okay, so but produces very low capacity as it goes to temperatures of the order of 80 Kelvin 100 Kelvin. The capacities are very poor. Okay, but everything, all the process is inside this one cylinder. And where do we use it? Definitely for cryogenic applications. So if you have very small LNG production plant, then we can use it. Or in case you have to store the LNG. So you have produced LNG by using some other cycle, and now you have to store and transport it to some other location, and you want to prevent the liquid from boiling off. So you have to continuously cool, matching the load being the heat leak from the ambient. So you can see such ships which are the transport vessels for LNG. And these LNG vessels will have such cryocoolers just to condense any natural gas which boils off because of heat leak. Of course, these tanks are all insulated, but even after that, you will have, because the storage temperatures are of the order of minus 170 degrees C. You'll always have significant amount of heat leak, and there will be some LNG which will boil off. So typically, I'll show you how it looks like. So if this is a tank, you will have the cryocooler located somewhere on the top. Okay, and let's say this is your liquid level. So there is some amount of vapor production. As it hits this cryocooler, it will condense and fall back into this tank. So that's why boil off liquefaction. So boil off will happen because of heat leak from the ambient, and this vapor will then come in contact with this cryocooler and it will re-liquefy and fall back. And if you don't have this, then the pressure inside this tank will continue to rise. Okay. Some niche applications are space applications and defense applications, mainly for thermal imaging or high-speed imaging. So your camera sensors, so they are not as small. The cameras are not as small as what we normally use, not even as small as the DSLR. So they are huge cameras. And for infrared imaging, if the sensors are cooled to a very low temperature, you get very good contrast. So many a times the high-speed cameras and infrared imaging devices that we use in our labs, the contrast is limited by the amount of cooling of the sensor itself. And so there are cameras which are available which require liquid nitrogen to cool the sensors. So this is a very niche application. So the cameras which are used in space or defense applications, they can also come with this compact cryocoolers. And this is one such mechanism which is shown here. So there are various ways of achieving the two piston motion that we have discussed. Okay, so you can have those two crankshaft as two ends. You can also have the crankshaft at one end, and you use one piston which is hollow and another piston which is solid. The solid piston goes all the way till this, one connecting rod which is solid and one connecting rod which is hollow. So the solid connecting rod goes all the way till this point, and the hollow one is connected to this piston. Okay, so this special drive is called a rhombic drive. You can see the animation in YouTube. So there are various ways of achieving the motion of the two pistons. And over here in this cryocooler, you can see the heat storage device is outside the cylinder itself. So gas actually goes from here, passes through this heat transfer media and comes over here. And again, it goes from here, passes through this and comes back here. Okay, in my previous schematic, you had the porous media inside the cylinder. So there are various ways of achieving this. A lot of innovation is happening in the Stirling refrigerator. Many people have completely removed this crankshaft and they have some kind of a vibrating element where the displacement is very less, but the number of cycles is very high. So a lot of innovations happening in the Stirling cryocooler segment, not on the thermodynamic aspect, but on the piston motion, how to achieve that in a more efficient manner, increasing the capacity in a very compact volume. So this is where the innovation is happening. Okay, and one of the company which is pioneer in this field is Honeywell. So any questions?
Sir, what is the porous medium there?
Porous medium, what is the material?
No, I mean, what is it doing?
Acha. So what it is doing is, see, we have to transfer heat which is rejected in this 2 to 3 process to the 4 to 1 process. So in 4 to 1, the gas is getting heated, and 2 to 3, the gas is getting cooled. So we have to transfer heat from this to this, but we do not have a provision for having a continuous heat exchanger over here. Okay, it is the same volume of gas which has to reject heat and then again get heated. So one way is to have some material which can store this heat. So as gas passes through this material, it heats up this porous media. So in a way, you can imagine that now this porous media is hot and it has stored the heat. Okay, but then when it comes back, so the idea behind this is when it comes back, when this gas now passes back through this media and goes to this volume, so that is the 4 to 1 process, the gas will flow through this porous media and the cold gas will become warm. That is what the porous media is there. So it is just providing the M into Cp to store. So it is acting as a reservoir, it stores and then releases the same heat. But since it is in thermal contact with the gas, it will also release heat during the heat absorption process. Okay, so these are the non-idealities which will kick in and it will reduce the CO2. So what we are assuming is it will only absorb heat during this process 2 to 3, and then when this piston is moving to this location, that is gas is expanding, there should not be any heat transfer between the porous media and the gas, and gas should only take heat from the refrigerated space. That is not going to happen. We will have some amount of heat being released by the porous media during this heat absorption process also. Okay, but the idea behind having this porous media is store and release. So what we always discuss in heat transfer classes is one type of heat exchanger where you have two continuous streams of fluid which are transferring heat. There are other way of transferring heat. Let's say you have a single passage only. Okay, and hot gas passes through this passage, and after some time cold gas passes through this passage. You can use this passage itself to store the heat from the hot gas and release the same heat into the cold stream. Okay, so these are the second type of heat exchanger. These are storage kind of heat exchangers. They are not steady heat exchangers. So you can have a honeycomb structure or any form of porous media, and when hot stream passes through it, the structure stores the heat and releases it when cold stream passes. So this is how the porous media looks like. As the name suggests, it's just porous material.
Sir, but
So
how
doubt is clear?
can this happen at very high cycles? Like number of cycles is, if it is very high, it will be instantaneous.
Mhm.
The heat transfer between the porous.
Yes. So that's why I was telling, no? So you will not have this entire process going like this. Okay, you will have a very small amount of heating in the porous media, and majority of the heating will happen in the compression process, which is not going to be isothermal. And then similarly, a very small amount of gas would be cooled in the porous media, and then majority of the cooling will happen when you expect heat absorption. So maybe only this much amount of cooling and this small amount of heating will happen in the porous media, whereas you expected to have this. So faster you go, worse your regeneration will become. Okay, so these heat exchangers are called regenerative type heat exchangers. So in fact, you may also see your process becoming like this, or maybe more skewed towards like this. So faster you go, worse your heat transfer will be. And more you will deviate from the isothermal compression and expansion also.
Okay.
So that's why the capacities for these systems are very limited. Okay, first of all, the capacity will be limited by the mass which is trapped. So m into, so this is what we discussed, na? M into. So this is still the ideal capacity. So the amount of mass which is trapped inside this cylinder will be low because air or any gas has very poor density. So if you want to trap lot of mass inside this two pistons, you will require a very large volume. That is one limitation. Okay, RPS. Okay, so you cannot go to infinitely high speeds also. So that is the next one. Okay, and the third one is, you will see one of the problem in tutorial, once you'll do, you'll realize that this T4 into S4 minus S3, which is the ideal case, that will also not happen. Okay, when your heat transfer processes are not as effective as what we are trying to achieve, that is effectiveness of 1. So if T2 minus T3 and T1 minus T4 are not what we actually are desiring, then also you will have heat transfer happening on the cold side. So you expected that the gas will pick up heat from the regenerator or the porous media, but it will, during the heat absorption process, it will release heat. Okay, so that will lead to some useless heating of the gas. So your T4 into S4 minus S3 will not be the refrigeration effect. It will be something less than this, because this porous media itself will now start releasing heat. So the main USP of this system is the compact nature of the system and the low temperatures it can achieve. Because there is no phase change in the refrigerant side, okay, you can use let's say air has certain components which can liquefy. So nitrogen starts liquefying at around -176. So if you want to achieve 80 Kelvin or so, then you will have to use helium as the refrigerant. Okay, so any refrigerant which does not undergo any phase change even at such low temperatures can be used over here. So air itself will have oxygen, nitrogen, which will start liquefying at such low temperature. So you will not be able to achieve such low temperatures with air as the refrigerant if you want to achieve 80 Kelvin, 100 Kelvin of that nature. So you will have to use helium. People even try out hydrogen, but hydrogen being unsafe is not commonly used. So we go for the next available element, that is helium. So this is where we'll stop. Please attempt the numerical because that will help you first to understand what type of questions you can expect in your midterm exams, and that will also connect what we have discussed, all the theory that we have discussed to the calculations that we can actually do based on our discussions. So I will quickly go through the MCQ problems of the tutorials. So these tutorials are uploaded in the class material section. So I hope everyone can see this tutorial 1. The first MCQ problem is in an actual refrigeration system, refrigerant superheat at the exit of the evaporator can occur due to which of the following reasons? You have large difference in temperature between the refrigerated space and the evaporator, or due to the presence of an LSHX within the system, thermal contact between the refrigerant and the ambient air due to poor insulation of the tubes, all of the above. Which one is correct? If you have followed all the class lectures, you should be able to answer these questions. These are just quick questions. In an actual refrigeration system, please read it again. Refrigerant superheat at the exit of the evaporator can occur due to which of the following reasons? Large difference in the temperature between the refrigerated space. Refrigerated space is your freezer or your indoor space, and the evaporator. Evaporator is your indoor unit, the heat exchanger, okay, or the freezer coil. So will it happen because of this large temperature difference, or it is because of presence of LSHX, or it is because of thermal contact between the refrigerant and the ambient air due to poor insulation, or it can happen because of all of the above reasons? Which one is correct? Your participation is needed. Come on.
Sir, all the above.
All the above. Everyone agrees? Everyone agree to this?
Sir, can you explain the A option?
A option.
Why it will occur?
Okay, so this is your internal regime. The question asks, in which case you expect the superheat at the evaporator exit to happen. So this is your internal regime. Your external regime is this. Okay, let's consider where you do not have huge temperature difference between the refrigerated space, which is the external regime, and the evaporator. You have very small temperature difference. Now, what is the potential? Let's say you have superheat at the exit. What is the potential of superheating? How much the refrigerant can superheat? Let's give some numbers. 17 degree is your refrigerated space temperature, and it comes out after coming in contact with the evaporator, let's say at 15. And the evaporator itself is at, let's say, 14 degrees. Very small delta T's. Okay, suppose there is some superheat in the exit of the evaporator. What would be the maximum amount of superheat? Just extend this heat transfer process. It can at best go to 70. Can it go to 18? Heat transfer is happening between the refrigerated space and the refrigerant in the evaporator. Can it go to 18?
No, sir.
It cannot. Okay. So if you have very small delta T's between the refrigerated space and the refrigerant within the evaporator, you will see the amount of superheat will also be very insignificant. And in such scenarios, you will see more or less the exit is close to saturated vapor region. Let's say it is coming at 30 and maybe cooling to 20, 25, whatever it is. Now, what is the amount of superheat it can theoretically sustain at the exit of the evaporator all the way to 30? So you can expect that the superheated vapor at the exit of the evaporator can happen if you have large temperature differences. If you have 1 or 2 degree temperature difference, your superheat can also be at best 1 or 2 degree. Be very close to saturated region. They're just limited by the external region. Theoretically, at all temperature difference, you can have some amount of superheat. Even half a degree temperature difference between internal and external regime, you still have that half a degree headroom for the superheat to happen. Is it clear?
Yes, sir.
Okay. Okay. Use of LHSI ensures which of the following: increase in COP, increase in refrigeration effect, suction to the compressor is in vapor phase, liquid refrigerant from the condenser outlet doesn't flash within the connecting tube before reaching the expansion device. What do you think? Which of these statements are true? We are using an LSHX. Which of these statements will be true? Increase in COP? Can we guarantee increase in COP?
No, sir.
No.
So first one is incorrect. Can we guarantee increase in refrigeration effect? Refrigeration effect is nothing but the enthalpy difference across the evaporator. So this is your heat exchanger. So your refrigeration effect is now this. And your standard cycle would have been this. So your refrigeration effect would have been this much for the standard cycle. So you gain some additional refrigeration effect. Okay. So let's be clear with the terminology. Refrigeration capacity is nothing but m dot into refrigeration effect, m dot being the m dot refrigerant. So refrigeration effect is just the enthalpy difference across the evaporator. So the second statement is correct. So I can guarantee increase in refrigeration effect. the third statement, suction to the compressor is in vapor phase. What about this? So no liquid. Correct. Yes. Now for fourth statement, you'll have to think a little bit. Liquid refrigerant from the condenser outlet doesn't flash within the connecting tube before reaching the expansion device. So what we assume is this is the exit of the condenser for a standard cycle, and this is the expansion device. So you will have your outdoor unit. So let's put some numbers for the standard cycle. 1, 2, 3, 4. Okay, so for the condenser, 2 to 3 is the process. Now the expansion process is 3 to 4. But there is a connecting tube over here. And you can have pressure drops over there. Okay, so if you have small amount of pressure drop within the tube which connects the condenser outlet to the expansion device, you will reach the two-phase region if you were using the standard cycle. So if you had saturated liquid at the exit of the condenser, even the smallest of pressure drop will lead to the liquid line itself having some vapor because you will reach here. Now what you're doing is you are subcooling it to this level. So let's say 3 prime. So the exit of the condenser, after that you have a heat exchanger over here. And what the exit condition is at 3 prime. Now if you have even small amount of pressure drop in the line, you will still remain in the subcooled region. I think we had discussed one of the advantage of the LSHX during the theory class. So if you have some small pressure drop within the connecting line, since you have subcooled, you have some headroom in terms of taking additional pressure drop in the connecting pipe. Yeah, so even statement D is also correct. Because at saturated liquid, smallest of pressure drop in the connecting pipeline will make the refrigerant to flash in the tube itself. Is this clear? Don't see the throttling process as a process which occurs only in a particular device, that is the valve or the capillary tube. It happens, throttling process will happen if you have any small amount of pressure drop. Okay, so even in the evaporator also you will have tiny amount of pressure drop. So the process line will not be horizontal, it will happen in this fashion. Okay, so similarly, the pipeline connecting the condenser outlet to the expansion device, remember most of the residential ACs, if you think, you'll have the expansion device in the indoor unit. So there is a long pipeline. Okay, consider if your condenser is kept below your indoor unit, then it has to travel a height also. Hydrostatic head will also be there. So you will have pressure decreasing as the refrigerant climbs up. So you can have pressure drops even in the connecting pipeline. So if you are already at saturated liquid, then smallest of pressure drop will take you into the liquid plus vapor dome. Okay. So that's why subcooling is also desirable effect. Doubts, questions? Okay. So the third question, in an actual refrigeration system, the temperature difference between the outlet and the inlet of the evaporator is Always zero, always positive, always negative? Can't say. So let's read the question again. In an actual refrigeration system, the temperature difference between the outlet and the inlet of the evaporator. Okay, so temperature difference between the outlet and the inlet of the evaporator. Temperature difference. This is the outlet of the evaporator in an actual system we are looking at, not the ideal one. And this is the inlet. So in an ideal system, the temperature difference is zero in an ideal standard cycle. What about the actual cycle?
Negative due to pressure drop.
Negative due to pressure drop, but you can have positive due to superheating. So our answer is point number D. Can't say. Which one is dominating? We cannot say. So if you have a very small temperature difference between the external and internal regime, you do not expect large amount of superheat. And hence there it is quite possible that the pressure drop may be the dominant one. But normally if you say, if you were to measure, actually measure the temperature, 99 out of 100 systems you will see that the temperature difference comes out to be positive. So the vapor at the outlet of the evaporator is superheated. And we will see why I am telling 99 out of 100 systems, because of the type of expansion device we use. Okay, for the time being, the correct answer is can't say. Because as you rightly said, there will be negative because of pressure drop. And I added that there could be a positive temperature difference because of superheating. So which one is dominant, we can't say. But as we move along in our course, you will see that there is a very special expansion device which we use. It ensures a positive superheat in the exit of the evaporator. Not positive superheat, it ensures a superheat. Okay, so we will see that. People who are confused, can you ask your questions, please? So why you are confused? I think most of the people are either tending towards B or C, isn't it? No? Everyone again agrees to point number D being the correct answer. If you don't participate, I cannot clarify your questions. Okay. Let's move to the next question then. If a refrigerant has large superheat horn, then use of LSHX will reduce the superheat horn. The sensible heat transfer within the condenser unit is large. Such refrigerants are not used in actual systems. None of the above. So you can have multiple answers correct, just like in question number 2. So you can have multiple answers correct. So if a refrigerant has large superheat horn, then use of LSHX will reduce the superheat horn. What do you think? This statement is correct?
No, sir.
No. Anyone else having a contradictory opinion about statement A? Okay. Okay, statement B is the sensible heat transfer within the condenser unit is large. Correct or incorrect? So what the first question states was, if you have a large superheat horn, so this is the superheat horn for the standard cycle. If you use an LSHX, you already now you send the superheated vapor into the compressor, your superheat horn becomes now with this. So it becomes even more larger compared to the previous case. So the statement A is wrong. Okay, now statement B is the amount of sensible heat transfer in the condenser is large if you're using LSHX. Oh no, sorry. If you are having a refrigerant which has large superheat horn, then you have large heat transfer, sensible heat transfer in the condenser. Large superheat horn. Okay, this is the superheat horn. So if this is large, it's another refrigerant has this kind of a nature. This is the superheat horn for the other refrigerant. So previously you had large superheat and now you have smaller superheat. So the refrigerant which has large superheat, the amount of sensible heat transfer in the condenser will be large. Is this true or false? This I think you can check from the graph itself. No? So majority of the heat transfer, yes, majority of the heat transfer in case of a smaller superheat horn refrigerant will have in the two-phase region, a very small amount in the sensible region. Whereas a refrigerant which has very large superheat horn will have majority of the, or not majority, but large fraction of the heat transfer happening in the sensible heat transfer region. And the extreme case we had discussed, no? Type 3 refrigerant where there was no superheat horn. In fact, after compression, we entered the two-phase region. So there won't be any sensible heat transfer in such a refrigerant. Now, such refrigerants, so refrigerants which have large superheat horn, they are not used in actual systems. True or false? So I gave you an example of ammonia. I think nobody cared to look at that question. So I asked you to perform an analysis of a standard refrigeration cycle. Let's say you use R134A as the refrigerant and use ammonia as the other refrigerant. Ammonia has a very large superheat horn. So what you so I just asked you to just check the temperatures that you get, the amount of heat transfer, all the cycle performance parameters. Please do that. Okay, and ammonia is one of the most commonly used refrigerant in cold storage systems. So superheat horn being large is not an issue, but superheat horn being so small that the refrigerant goes into the two-phase region during the compression, that is an issue. Superheat horn being large leads to large or high temperatures at the discharge. Those issues are there. But if it reaches in the two-phase region, that is the biggest issue which we don't want. So there's nothing which stops us from using refrigerants which have large superheat horn. So none of the above. So but we have B, answer number B, which is, or statement B, which is correct in this scenario. Due to the presence of pressure drops in pipes and valves of the refrigerant loop, compressor work input increases, refrigeration effect increases, compressor discharge temperature increases, and none of the above. Again, you have to sketch the process. So consider a standard cycle consider the actual cycle where you have pressure drop. Okay. You have pressure drop in the evaporator. You may have pressure drop in the valve itself before it enters the compression chamber. Okay. So this question doesn't ask us about the isentropic efficiency of the compressor. It just talks about the pipes and valves, all those things. Okay. Similarly, over here also you will have, so you will be compressing not to the same pressure which you were expected, but you will have to compress it to a higher pressure, because then again at the discharge of the compressor you will have some pressure drop, and then you will achieve your own desired pressure. And then again in the condenser side you can have some pressure drop. Okay, so it just talks about, it doesn't talk about the isentropic efficiency as long as, so it is just about the presence of pressure drops in pipes and valves of the refrigerant loop. So which of these things will happen? Compressor work input increases, definitely. Refrigeration effect increases, or it remains same or decreases. Can you comment on that? Can you comment on that?
Decreases.
Decreases.
Decrease.
Okay. And then compressor discharge temperature. Can you comment on that? Compressor discharge temperature is this one, discharge from the compressor. Standard cycle discharge. If you take into account the pressure drop in the evaporator, this is where you reach pressure drop in the evaporator and in the suction valve of the compressor. This is where you. Okay, so you will see that lower suction pressure actually increases the discharge temperature. Okay, so if you are operating your evaporator at a lower temperature, after the compression process, you will have significantly higher temperature than if you had compressed the gas from a slightly higher suction pressure. Okay, it is again dependent on the amount of work input. So you have to provide more work for the compression process, and that leads to the heating of the gas. And it is evident from the cycle also. Okay, so this refrigeration effect increases is correct or incorrect? So this one is correct, A is correct, B is correct or incorrect? Okay. Why with such poor conviction?
Incorrect.
Okay, and C is correct. So A and C is correct. So please have a look at these numerical problems. We have 1 week to have a look at these numerical problems. People who are comfortable with the tables, they can have a look at this table which is provided at the back. And people who actually want to learn EES can actually write the code, just vary the parameters, and you'll be able to answer all these parts of the problems. Okay, so I hope you know the conversion between R-ton and kilowatt. So even if you don't know, you can get it from Google, or if you're using EES, it will give you the conversion. So please have a look at these problems. There is another tutorial which I have given. This is for the air cycle. think very few problems. So question number 3 is a Stirling refrigerator is an open cycle, closed cycle used in aircrafts. So we know it is a closed cycle and used in small capacity car coolers. B and D. Reverse Brayton cycle is preferred in aircraft air conditioning because synthetic refrigerant used in VCRS are not environment friendly. Definitely that was not the concern when people started building the air conditioning unit for aircrafts. VCRS requires a separate closed loop system which increases the weight of the aircraft. The engine compressor can be used to drive the air conditioning system, making it more compact. The engine cannot provide sufficient power to run a VCRS compressor. So A and D. Do you think that the engine is not powerful enough to run a VCRS compressor? Definitely not. So A and D are incorrect. A VCRS system requires a closed loop system and you have to carry that closed loop system always along with the plane. And that's why when it comes to halt in the ground, we use an external VCRS system to provide the air conditioning instead of people say that why not use a battery and drive a secondary VCRS loop and provide the air conditioning. But then again, you'll have to carry that. So less payload. And definitely engine compressor can be used to drive the air conditioning system. So reverse Brayton cycle is preferred because the engine compressor is driving a part of the air conditioning system. So the amount of compression partly is directly taken from the engine compressor. Suppose we choose to have a VCRS system. How will you drive that VCRS system with the engine? Can anyone tell me? Just an hypothetical question. Suppose tomorrow I have a startup and I tell that I can create a very compact VCRS system. And I will want to put VCRS system in the aircraft. And how will I drive that VCRS system from the engine? Or for that matter, how are the light and the electronics powered? In an aircraft. There's so many electronics, so many gadgets to be powered. So find out how those electronics and how these auxiliary systems are powered from the engine. Yeah, because engine is just producing thrust and producing the power required to run the compressor. So how do you get the electricity? Find out. Okay.
Sir, we can use the turbine output.
Turbine output. So then we require a generator.